Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast. My goal here is to find the best of the best in their fields, the people that are really exceptional, that are doing really novel things, and not just, another one of their field. So I've interviewed this person before. It's Preston J. MacDougall, Ph.D. He's an author and a professor at Middle Tennessee State University. Something really interesting. It was about, how the electron clouds and atoms and molecules, obviously govern their chemistry and a lot of other aspects to them, which he'll get into. But Preston, welcome. How you doing?
Thanks, Richard. I'm doing well, considering I'm working from home quite a bit, and lectures in the class will be online starting next week. So it'll be a new experience for myself and the students, but I'm looking forward to the challenge.
Yeah. So tell me a little bit about your research in your own words, because I know that, you'll be able to express it better.
Okay. Well, in your opening, you mentioned that it seems rather obvious that the chemistry is dictated by the electron cloud, electron density in a molecule, and that may be true to you and I, but it's not obvious to everybody. A lot of chemists still rely on what's called the orbital model. This is a very convenient model that comes from quantum mechanical calculations, and it's compelling because we use it to teach students, to help students understand the electronic configurations of atoms on the periodic table, why the periodic table looks the way it does. It's very conveniently explained by the orbital model, and this model we can get into if you want, but it's an old model, been around for over about a century, and it's been extended to molecules as well as atoms. And people are comfortable with what they learned, and so a lot of chemists really they want to try and understand molecules in terms of these these orbitals, which are really non-existent entities.
Right.
They cannot be measured.
They're probability clouds, right?
Well, they're probability clouds for a single electron. And that's assuming that electron is uninfluenced by the motions of all the other electrons. In other words, they're not correlated with one another. And of course, electrons repel one another, and they're very tight quarters. They exist on the same atoms, which are small things. So they are very strongly correlated. And that means you can no longer imagine the distribution of a single electron in its own three-dimensional space. So
in terms of electrostatics, I mean, if you can't see an electron cloud, I would figure you could feel it. You could feel the if you're approaching it with a negatively charged object, you would feel the repulsive force that would change. So in that way, you can envision a surface to it. Am I on the right track there? Is that what you've been looking at?
Well, electrostatics are certainly a very important part of chemistry. Everybody's experienced that. Some things are, like, take something out of a dryer, some things stick together, and there's a little crackle when you pull them apart. So there are electrostatic forces between molecules, but the problem is when molecules or atoms or molecules get very close to one another, there are other factors, quantum forces, which dominate the electrostatic forces. So when you mentioned getting close to an atom with some sort of probe, you imagine that there was a surface that you might feel because of the electrostatic forces, and that surface you do not experience that particular surface. Atoms and molecules, when they approach each other, do experience a repulsive wall, and we can feel that when we try and put our finger through a real wall. Where there's a repulsion, it prevents our finger from going through the wall. So that is caused by electron clouds repelling one another, but that can happen between two atoms that are neutral, such as two helium atoms. And so it's not strictly electrostatics. There are quantum mechanical forces in operation simultaneously, and that's what makes quantum chemistry so complicated. It's not just a simple matter of electrostatics, two point charges interacting with each other. It's the wave mechanics of each of the atoms comes into play, and then it becomes a multidimensional problem.
Well, I mean, as I understand it, for a given atom, you envision the nucleus as this tiny little ball, and then way away from it, a football field or so away, is the electron cloud. But so, what does it look like if you have let's say, like a gold ion or a gold atom? It has a bunch of different orbitals. I'll just call them. What would that look like? Do the orbitals sit concentrically outside each other, and then the electric field of each, does that influence each other where it makes like this, I don't know, this like lumpy shape to it if it had a shape on the outside of the atom? Like, have you tried to envision that?
Well, no, yes, we do envision it, we calculate it, we display it, and there are ways to measure those lumps within an atom. We talked about that briefly in our previous podcast where I discussed picotechnology, the subatomic structure of an atom measuring in 10 to 100 picometers. A picometer is 1,000th of a nanometer. So what you mentioned, imagining these orbitals, but again, when we get back to the orbital question, when students learn chemistry as freshman students, the first thing they learn are the atomic orbitals, the s orbitals, the p orbitals, the d orbital, and they see pictures of these, and they're in all the textbooks. And as I mentioned before, they're useful for explaining why the periodic table looks the way it does, the shape it has. But then in the same year, by the end of the freshman year, when students need to understand bonding, they start to introduce what are called hybrid orbitals. Now, these are needed to conveniently explain why, say, the bonds in methane are at tetrahedral angles, 109.45 degrees, whereas the orbitals that they just learned about a few months ago, the p orbitals, are at 90 degrees of separation. And the s orbitals are spherical, so they don't have any directionality at all. So these so-called hybrid orbitals were invented, as all orbitals are invented. They're mathematical entities that don't really apply to real atoms and molecules with more than one electron. But they were invented by Linus Pauling almost 100 years. And so they learned these hybrid orbitals, and they look different. That's the important thing. So when you say, what do the electron orbits in a gold atom in a molecule look like? Well, which paradigm do you want to use? In one paradigm, they look like p orbitals, the same as you saw when you study the hydrogen atom. They're exactly the same shape. Or do you want to think about the bonding orbitals that you learned about when you learned about molecular shape, the sp3 orbital, sp3d2 orbitals? Different electrons would require a different shape. So rather than relying on the orbital picture, again, I prefer to look at the probabilistic picture, and that is any electron in a gold atom has a certain probability of being found at a certain point. And that is what we call the charge density, cloud density. And that density is a maximum at the gold nucleus, and it falls off monotonically as you get towards the surface between the gold atom and whatever it's bonded to. And so in between the nucleus and the surface with another atom, it's pretty boring looking. It looks basically like a mountain with one tall peak and falling very steeply down to the valleys on the side. And you don't really see any indication that gold has many shells, fifth row of the periodic table. So it's got a lot of shells and a lot of structure to it. You're clearly imagining there's all this nuance to this cloud, but it's not there. It is just a peak falling down. But then when you look at the subtle wiggles, that's when you look at the second derivative in 3 dimensions of this density. Then you see the shells and the lumps near the bonds, and the structure is much richer. So yes, that's what I prefer to visualize. And experimentalists, when they diffract X-rays off of crystals, they can, if they collect enough data and get the error down to a low enough value, the statistical error down to a low enough value, they can see the shells and the lumps where chemists imagine the bonds to be.
I was thinking about it wrong. I was thinking about it statically, but I forgot that I guess all bonds, depending on temperature and the type of bond, they have a certain angle, they have a vibrational frequency. So in a short time lapse shape, I guess the outermost of a given molecule change. If you look at it in a short enough time scale, you would see probably a very dramatic change in shape, right?
Well, if you could do that, that is a very large challenge, because the vibrational timescale of a molecule is typically the vibrations take less than a trillionth of a second. and
Oh, okay.
very, very hard to do an experiment in a trillionth of a second. So what chemists do is they cool the crystal down very, very low temperatures, either with liquid nitrogen or even liquid helium. It's really good to get the air down. I mentioned getting the air down. They will blow helium from a liquid helium tank onto the crystal to get the temperature down to a stable 20 degrees Kelvin, minus 250 degrees Celsius. And at this temperature, yes, the molecules, the bonds are vibrating, but they're vibrating in one single mode called the 0-point motion. And that is a very harmonic motion, and it can be, you can deconvolute the cloud. Basically, just sort of like if you have a camera, all these cameras have built-in software to remove vibration. If you're holding a camera and your hand is vibrating, if it's a pretty regular vibration, you can erase that. You can deconvolute it so that the image does not vibrate. This is common technology on cameras. So X-ray diffractionists can do the similar thing if the molecule is vibrating in this one very well-defined mode. And then it looks like it's standing still. And of course, you're right, it is not standing still. The bonds are vibrating, but it's vibrating in a very harmonic way that can be subtracted out. That allows you to do the experiment, which takes, used to take days to collect X-ray diffraction data to get a good error, a low enough error to measure the charge density. Now it can be done in minutes. But still, a minute is a long time compared to the vibrational frequency of a molecule, which is less than a trillionth of 1 second. So yeah, when we do that error analysis, we see a static molecule. But you're right, the cloud is vibrating, but we try and simplify it.
Bond vibration and things happen at a typical temperature you deal with, for a living, or even for most applications, is the vibration of the bonds important. What factors are important in discovering that govern, maybe the things that govern chemistry, molecular interactions like that we don't know, and stuff like that out?
Yeah, that's a very good question. So yes, it's, for instance, in proteins, for example, proteins have what's called an amide bond, and it involves carbon, nitrogen, and oxygen. So at this amide bond, the nitrogen is involved in what's called a double bond to the neighboring oxygen atom, and if that bond is that bond, I don't want to get too much technical detail, but that bond can conjugate with the neighboring bonds, and it's because of the conjugation, this bond is planar. So in other words, the nitrogen is all the atoms around it are form a plane. Now you can make that nitrogen a pyramid. You can parameterize it. If you do that, then the structure, the shape of the cloud changes, and that changes the chemistry, because you can create a lump where there was no lump before. So yeah, that's because these, as you say, these vibrations are happening all the time. It's not just a bond stretching; it's also 3 or 4 bonds, sort of an umbrella. It's called an umbrella motion, where things are from a pyramid, then they flatten out and they go back to the pyramid. This happens, trillion times a second, and so we can monitor the change in the subatomic features using this second derivative analysis I talked about previously. You can see new features pop up in a certain arrangement of the atoms. And so you can imagine when a molecule is undergoing a reaction that the reactants force these changes, not just temporary changes which happen in a vibration, but force permanent changes in an atom, such as in a catalyst. You can force an atom to bend, become pyramidal instead of planar, and so the catalyst will then force a change in the structure of the subatomic structure of an atom. It will create a reactive site that wasn't there in the uncomplex molecule. So yeah, your question.
Oh, that's interesting. Okay, I see what you mean. So in a way, it could lay bare parts of the molecule that weren't before, or it could build up charge and deplete charge in a certain area,
that's right,
allowing a bond to happen that wouldn't normally happen, right?
That's right, within an atom, yes. And atoms are in molecules, so yeah, the environment of an atom can cause a geometric change that basically itself results in a creation of a reactive site, either a hole or a lump. that wasn't there before. Or it can make a small hole bigger. A lot of atoms have tiny holes in their what we call their valence shell, but they're not big enough to undergo reaction in another atom. But you can, by bending it or bending the atoms around it, you can enlarge the size of the hole, and we can study that with computers. That's the beauty of quantum chemistry tools, is you can run
This is cool.
Oh yeah, it's a lot of fun. You can.
Are there does this suggest that there's non-contact enzymes? Maybe other atoms or molecules that can get so close in proximity to a given number of reactants that cause them to deform so that they can react, but without contacting?
Well, I think what you're asking is, when you say contact, I think you're implying forming some kind of strong interaction. So yeah, most enzymes are in fact non-contact. They really just get close enough to disturb a molecule without actually forming a covalent bond or forming a permanent bond. Some catalysts do form a bond, and then the reaction occurs, and then that bond is broken. But many catalysts work by just being close enough that a molecule is deformed enough to change its reactivity. The reaction happens, and then it releases all contact. So when you say contact, there's chemists imagine different kinds of contact. There's two atoms that form a covalent bond. This happens with glues, cements, contact cement, permanent glues. Then we also have sticky pads, which are reversible stickiness, sticky notes from 3M, or the foot of a gecko walking up a glass. The gecko's foot easily comes off the glass just as easily it goes on. These are called non-covalent interactions, and they're really the what's happening in most catalytic processes. Atoms are close enough that they form a non-covalent contact. It affects the molecule, but it doesn't form a permanent bond that is hard to break.
This sounds like a whole new language of chemistry, like Braille. The chemical equivalent of Braille that would describe a whole bunch of phenomena that maybe weren't understood before, like the action of catalysts. They're not necessarily bonding, and maybe that's why they're not consumed. They're just getting close and maybe temporarily bonding, or just maybe even close enough to disturb the fields of the molecules that you want to interact, and maybe that's what's causing their action.
It is. That is exactly how a catalyst works. And if it can do its job by just deforming a molecule enough to make it react and then let it go, then it will last forever. A lot of things happen. There's poisons. A catalyst, a reagent is never pure, totally pure. There can be poisons and these things will form permanent bonds to the catalyst. Just like when you inhale carbon monoxide, instead of the carbon dioxide and oxygen that's in air normally, if there's carbon monoxide, that gets into your enzymes in your lungs, and it doesn't come off. It bonds to the hemoglobin molecules that normally attach oxygen and release it, but carbon monoxide doesn't release. Bad news for you. Catalysts don't normally last forever because real life is not perfect, but a good catalyst will last a long time and do its job for hundreds of thousands of what we call turnovers. Time to replace it with a fresh catalyst.
So what would chemistry look like in an oscillating magnetic or electric field? Would that change the surface characteristics of the molecules to allow different types of reactions to occur?
That's an interesting question. Of course, a molecule itself has oscillating electric and magnetic fields as electrons whiz around the atoms. But if you're talking about an external field that, say, chemists can control, then that's different because that is hard to penetrate. If you have a large magnet on the outside or a large electric field, makes your hair stand up, for instance, that field dampens very, very drastically as you get inside tissue and inside cells. So it's very difficult to control the chemistry of an atom or molecule inside an organism or a large sample with external fields. But the molecules themselves have these fields, we try to take them into account as best we can with our quantum chemistry tools. So when you talk about oscillating fields, it depends whether it's an internal field or an external field and what the frequency of the oscillation is. And sometimes it can be a permanent field. Like if you go into an MRI machine, is not oscillating. It's a permanent magnetic field that radiologists take advantage of to probe the chemical environment of protons in your body. Those protons are in permanent, very stable magnetic field, and how that disturbs the nuclei and hydrogen atoms is how we get an image, and that MRI image that shows that hydrogen is part of a molecule in a tumor, or that hydrogen is part of a protein in a healthy muscle. So we chemists and radiologists do take advantage of the effect of magnetic and electric fields in interesting ways. I'm sure new ways of leveraging electric and magnetic fields will be thought of in the future.
Yeah, it just feels like there's a ton of work that needs to be done to understand this, to incorporate this new understanding. I mean, now I understand. I don't know why exactly, but now I understand. Okay, pressure. That's why. Here's another reason why it would affect reactions. Temperature. pH.
Well, you mentioned pressure.
All these things.
Yeah, you mentioned pressure. That's another whole other interesting dimension of modeling. When chemists started doing calculations on molecules with quantum mechanics, they had the molecule by itself. In other words, we treat it as a gas in a gas, because gas particles are not in contact with other particles. And so that's the way it was usually done. And so a lot of the original calculations, we were really studying modeling molecules in a gas. But then people say, well, molecules really do most of very often, their reactions are done in solution or even solid state reactions. So then they started figuring out how to model a molecule in a condensed environment, such as in a liquid or a solid. And once you do that, you have contacts with other atoms. Well, maybe those contacts are tight up and have lots of force, as in a high pressure environment. So chemists started modifying the pressure that atoms were in, exerted on by their neighbors, and very interesting things happen. We talked earlier about you can create a reactive site by bending a nitrogen in a protein. Well, people have done some calculations. I haven't done any of these myself, but I've read a lot of interesting papers, again, by my advisor, Richard Bader. He did the first one, where when you change the pressure, you can see the electron cloud change. And there have been some fascinating results explaining odd, unusual behavior that's seen for elements even when they're compressed in what are called diamond anvil cells. I don't know if you've ever had a show on diamond anvil cells, but these are very interesting
what is
devices.
That?
Pardon me?
Yeah, what is that? Tell me about it.
Well, when chemists started exploring the effect of pressure on chemistry, they had to basically create a gigantic vessel that could withstand high pressure. So these were usually large stainless steel vessels where they would crank up the pressure. It'd be like a bomb, basically. If you had to be very, very, very strong steel, because there's high pressure inside, and if it failed, it would explode. So these are very bulky instruments and devices, and very expensive. But they couldn't get very high pressures because they'd explode if it got too high. So General Electric did some very interesting research on this in the 1960s, where they took organic matter and converted them into diamonds. And people have scaled this up to make synthetic diamonds, again, with these very high pressure stainless steel pressure devices. But some interesting physicists, some very thoughtful and innovative physicists in India thought, well, pressure is force over area. We only need these high forces at General Electric because there's a huge area. They have these man-size pressure vessels. What if we make the area very small, say the size of the point of a diamond, and if the area is small, then to get the same pressure, we only need a small amount of force, because pressure is force over area. So if you make the area very small, the force can be correspondingly small to achieve the same pressure. So he made this diamond anvil. Basically, it's two diamonds that are pointed at each other, and there's a little gasket. Usually it can be a rubber gasket or some kind of other material, but it's very small, and it basically encircles the point of contact between the two diamonds, and then just hand-applied pressure. This first thing was a little wooden screw. Just with your hand, you could create pressure equivalent to the center of Jupiter, something that had never been achieved in the largest pressure device by General Electric. This was done with a handheld device. And so these diamond anvil cells are beautiful because diamonds, as you know, are transparent. So you can watch what's happening inside this, between the points, when the pressure is going to the pressure equivalent to the center of Jupiter. You can see what's happening because the diamonds are transparent. And it's been phenomenally interesting discoveries on the nature of matter. Sulfur becomes a metal. Hydrogen gas becomes a metal. And again, there are changes in the subatomic structure. The reactivity will change. And we haven't studied yet, as far as I know, how these atoms change at the subatomic level, but people have studied, they know that changes happen because the color will change, or it will go from transparent to opaque, like hydrogen is a transparent gas, but hydrogen metal is expected to be an opaque, shiny object. So yeah,
is there enough sophistication in the shapes of molecules and their disturbances to call it a language, or do you think there's a very small subset of possible shapes, or is there a very big universe of possible shapes and interactions?
Interesting question. If you're talking about molecules, the range of possible shapes is fairly limited, and there are names associated with all of them. And they can be something that can be triangular, it can be planar, pyramidal, it can be tetrahedral. So there's not that many possibilities for the shape of one atom as far as the arrangement of its neighboring atoms. But if you go into not just the arrangement of neighboring atoms, but the arrangement of critical points or features within the atom, then the complexity goes up very quickly, and the number of possibilities rapidly escalates. And I'm not sure there is no language for that yet, and I'm not sure if it would be practical to try and come up with one. Might have to be just some numerical nomenclature. That's an interesting question. We haven't yet been explored. We're just trying to borrow the language from molecules, and that quickly becomes insufficient. And so we resort to images. And so here's the structure of here's the subatomic structure. You can see there's holes here, here, and here. So we depict them with images, three-dimensional images. It's very difficult to describe them with words. So to answer your question, I think it would be difficult to describe all these possible shapes with simple words. And this reminds me of enzymes. Biologists, first they had names for enzymes, like carboxylase or phosphorylase, that described what the reaction was. And the same with genes. Then they quickly became too many of them. There's tens of thousands of genes for proteins. So now molecular biologists, they just have basically the names for genes have no meaning. It's just numbers and letters, and that's how they're referred to, because it'd be just too complicated to try and give them words. So I think it might be something similar.
So what are you able to postulate? So if a molecule has holes, is a hole the same as an active site? Like, supposedly we know, okay, this molecule has an active site, and here's where the receptor is, and here's what it looks like. But now this is another dimension to shape. So is this revealing on a given molecule, let's say that you're studying hidden receptor sites because of the holes? Are they located in the same spot as, what's traditionally thought as the receptive part?
Yes. But that hole was probably always there. It just wasn't large enough to engage in a reaction. So I think we're going to have to learn more about when you reach a critical size. What are the critical properties of these reactive sites, these features that make it critical, past the critical point where a reaction is more likely to occur? So that is something that needs more investigation to try and determine thresholds, for instance. But yeah, there obviously is a threshold for a reaction to occur, because we know that some reactions don't occur until a certain temperature is reached, or you change the neighboring atoms to a certain type of atom that disturbs it marginally more and makes it suddenly it reacts where the previous bonding it did not react. Yeah, there are thresholds, but that is to learn more about them, flesh them out, is going to require a lot more research.
Are any of these these shapes, are they all just like, I don't know, melted ice cream, and they're not really clearly defined, and you have like just lumps and holes, or do you see any complex geometries or shapes that really shock you?
Oh yeah, you see some very interesting shapes. I did an interesting calculation on a catalyst that's used to make high performance plastics, and the shape of the molecule was pretty familiar to what freshman chemists see when they study trigonal bipyramidal molecules that have familiar shape. But when we got to the shape of the features within the atom, I saw a very interesting shape inside the atom. And some of them are very common, have a tetrahedron. For instance, I already mentioned methane has a tetrahedral shape. If you're playing dice, Dungeons and Dragons, and the odds of getting slain by a marauder are 1 in 4, you don't want to use a regular dice, which has 6 numbers on it. So you use a tetrahedron, which has 4 numbers on it. So a tetrahedron is a very familiar shape to chemists, and a lot of atoms, if you look inside their core, we saw a tetrahedron inside the atom. So it's a tetrahedron inside a tetrahedron. And that's actually very common because you might have heard of the octet rule. So a lot of atoms have an octet, which has 4 pairs. So a lot of atoms that have an inner octet in their core, we see this tetrahedral arrangement. But then sometimes you have more than an octet in a shell. So I saw this was a niobium atom. And if you're familiar with the Pink Floyd Dark Side of the Moon album cover, you've seen a prism, which is triangular, but it's a triangular prism. So it has 5 sides. It has 3 rectangular sides and 2 triangular sides. And I'm referring to the prism on the Pink Floyd Dark Side of the Moon album cover.
Okay.
And it's a familiar shape. So that has 6 vertices, okay, because there's 2 triangles connected to each other. And that's what we saw. We saw what's called a triangular prism. But it was not a regular triangular prism, because in a regular triangular prism, all 6 vertices are the same. Like if you have a dice at Las Vegas, all 8 corners of the cube are the same, unless you're working with a rigged casino. Okay, so all the 8 corners of a regular dice are the same. So all 6 faces are exactly the same. They're the same size, all the angles are the same, there's different numbers on 1 through 6. So in this triangular prism, you'd expect these 6 vertices, these 6 corners, to be the same if it was regular, but they were not in this case. There were 4 large lumps and 2 smaller lumps. Other than that, it looked like a regular prism. And this was interesting because in this particular atom, there was an octet that gave you the 4 large lumps, but there were 2 extra electrons that were unpaired, and because it was magnetic. So they were unpaired, so that we could rationalize that as there being the regular octet plus 2 unpaired electrons. That's why they were smaller, because a pair of electrons has 2 electrons, where an unpaired electron is a single electron. So that's an example where we saw a very strange shape, but it wasn't completely new, because it was a trigonal prism, which we've sort of seen in regular life, and some molecules. Very rare, but some molecules are known to have a trigonal prism shape. I'm talking about.
What would a noble gas look like? Have you modeled that? And then what if you took an atom and you slowly ionized it, took away electron by electron by electron, and calculated it and looked at the progression of shape change? Maybe this would give you an idea on why the octet rule is there. What makes something complete? Is there a shape component to it that makes it particularly stable or complete?
Yes, very good question. If you start with the beginning, if you look at the electron cloud in a noble gas as a gas, it is perfectly spherical. There are no distortions in this. It looks a beach ball. It's a perfectly spherical shell. Now, if you start to remove electrons by ionizing it, then yes, you will see distortion if there are neighbors to sort of pin directions. And people have done calculations like this, and it's very interesting. I'm not sure about if you're going to get a really deep understanding of what causes the energetic stability of a noble gas, with its octet just by looking at the shape of the cloud, because the energy is there's a theorem called density functional theory, which says that the energy of an atom is uniquely determined by the distribution of its electrons, but with so-called functional. That functional is what translates the cloud into the energy. And chemists have been searching for this functional for 60 years now. And there have been 2 Nobel Prizes given for attempts, but we don't know the functional. So we can't just look at the cloud and determine the energy. This is like a holy grail for physicists and many chemists. But we can certainly correlate how the changes in the shape parallel changes in the reactivity. And since you mentioned noble gases, let me start there. If you're familiar with the periodic table, you know the far right column has helium on top and xenon on the bottom. Unless you have a brand new periodic table, it will have OG, element 118, which is below radon. Sorry, radon used to be the bottom right corner, but now we have OG. I like to say it's the real OG. This is the heaviest gas known. It's one of these super heavy elements that only exists for fractions of a millisecond. So anyways, xenon used to be, until radon was discovered, xenon was the bottom right of the periodic table for a century. And didn't make any compounds. Helium doesn't make compounds. None of the noble gases make compounds. And if you look at periodic table, when I started studying chemistry, the periodic tables at the top right, they were labeled that they were called inert gases. That was what they were called in textbooks and periodic tables, because they were believed to be completely inert. But in the 1960s, chemists at British chemists who worked at the University of British Columbia thought, well, it's not that hard to use lasers to ionize a xenon atom. So we should be able to remove it with chemical reagents. And nobody ever tried that before. And so he tried it, and lo and behold, xenon made compounds with fluorine. And the rest, then shortly after that, a whole flood of xenon compounds were made. They made crystals of them. They studied the shape of the molecules, and they were beautiful. And a Nobel Prize was given to this chemist. But to answer your question, yes, we can calculate the xenon atom, which by itself is a beach ball. But when you bond it to fluorine, or 2 fluorines, or 4 fluorines, or 6 fluorines, you can see that the shapes change, and the xenon atom slowly loses its cloud to the fluorines, and you can study the shapes and how the reactivity of the xenon, as you pull electrons away, you can understand why it changes. So yeah, we have done that. I published a paper on krypton compounds with a chemist that used to work across the hall from me at McMaster University in Hamilton. And he worked with krypton and xenon all the time. And these are very dangerous compounds to work with, because although they can be coaxed into making compound and crystals, they really want to be gases. And so when a crystal turns into a gas, that's called an explosion. So they would always work with very small samples. They would keep them at low temperature, store the liquids or the compounds at low temperature, and be very careful touching them with your hands, because your fingers are warm, and just the warmth from your finger touching a test tube with a tiny crystal can result in explosion and loss of fingers. So there would always be bangs. I don't want to mention this professor's name because people can figure it out, but he was doing excellent chemistry, exploring the chemistry of these what are now called noble gases. So, sometimes they have very useful applications. Krypton, which is above xenon, the periodic table, below argon. Krypton and even argon fluorides make temporarily stable compounds that are used in etching high density chips for the computer industry, large with very small features. I think they're in the nanometer range. I think 19 nanometers, something like that. I forget the exact dimensions, but they use so-called excimer lasers that use compounds of krypton and even argon, and some of them, to make these very small features, because the wavelengths of the photons are small enough to make very small features. So nobody thought we would get anything interesting chemistry out of the far right of the periodic table, because we didn't think they formed compounds. Then they formed compounds, and we thought, well, those compounds aren't very useful. And now we make computer components with the compounds made by those very elements that we thought were inert.
Can become kryptonite if you're not careful.
There you go. Then you get into science fiction as well. So yeah, some part of the periodic table that we thought was completely boring is fascinating and has huge world-changing applications. So who knows? You never.
What do you think? What do you think is an important factor? Is the density of the electron clouds in a given molecule, or is it the distance from the nucleus? Which one do you think is more important?
Well, it all can be important. And generally, I think what is really important, and it's a very difficult question to answer because we're still just at the beginning stage of this research. Still,
well, I guess a better question is how do the two influence chemical reactions? Density versus distance, or radius away or distance away from a given nuclei.
Okay, well, let me start with the distance. The distance is kind of set by the element. For instance, if you're working with a carbon atom, all of its valence electrons, the electrons that do the business of a carbon atom, those are all roughly the same distance, about half of an angstrom from the nucleus. And it doesn't change very much from one compound to the next, whether it's a diamond on your finger or a protein in your finger, that the distance is pretty set for a carbon atom. What does change is the amount of concentration, whether the electrons are very highly concentrated or very strongly depleted in a deep hole. To answer your question, I would say it's the amount of concentration, local concentration and local depletion at these in these subatomic features that really stay the same distance for a given atom. Now, of course, a silicon atom is bigger than a carbon atom. It's got an extra shell on its electronic structure. So all the electrons that do the business of silicon are further away, and their chemistry is quite different than carbon. So I don't want to compare apples and oranges or carbons to silicons, because chemists don't like to do that, because there's really huge differences between the chemistries of atoms that are even neighbors on the periodic table. But so I would sort of say distance is probably not that important. What is more important is the extent of concentration and depletion at the site of these reactive site. And that's something we can calculate with computers very accurately, and we can even measure that with very carefully done X-ray diffraction experiments, good crystals at low temperatures. We can actually measure these properties, these concentrations, and that I think is what really ultimately determines it.
Yeah, I feel excited for you. I feel like if I were you, I'd be calculating like crazy, all kinds of stuff, because there's so much newness,
Well, it is new, and you should tell your podcast listeners that there's always openings in Ph.D. program at MTSU. So right now, my last student just graduated this past December. He did his thesis on carbonyl chemistry, looking at the topological features in the charge clouds, but adding in machine learning to help see how we can use machine learning to make predictions based on these topological features. And he's now teaching at a college. So there's an opening for research in this area as we speak. But it is exciting.
Yeah, and it's funny, the square peg in a round hole thought in my head keeps coming up. I know that doesn't apply here, but it applies in the way that, I guess, if you knew the exterior, I'm going to call it shape of molecules, and how they react under different disturbances, how they change shape and the extent to which they can change shape, it would reveal a lot about the chemistry of that particular molecule.
Yeah, the square peg in a round hole, that's not that, that is a very good analogy. We haven't explored that so much, but certainly that's a very popular analogy in biochemistry, where the lock and key model. Some drugs work because the same reason some keys work and other keys don't. So that's a very popular and useful analogy at the molecular level. And who's to say that it doesn't apply at the atomic level as well? Maybe some reactive sites on some atoms have, besides their size, maybe the shape of these reactive sites is a crucial factor in determining whether it reacts with another atom or not. We haven't really explored that. We haven't explored that.
Yeah, definitely.
An interesting idea. I write it down.
Well, cool, Preston. Good. Yeah, Preston, this is an awesome call. I don't know why. I'm just like, I think it's so cool. It's just a very fundamental difference in how chemistry was taught to everyone versus what the reality is, and it's a lot more rich. So what's the best way for people to find out more? And do you have, pictures of calculations you've done and shapes? Can you send them?
There's a lot in publications that some of them are available freely online. More and more journals are going to open source publishing. So, and that's maybe the best place is there's a website called ResearchGate, where a lot of scientists is sort of like LinkedIn for scientists, where people upload all their publications and presentations, and you can ask technical questions about various disciplines in science. So a lot of my publications can be downloaded for free on ResearchGate. So that's probably the best way. It's not just for me; it's true for a lot of people.
All right. And you have an unusual name, so Preston MacDougall. It should be pretty easy to find you too.
There's not too many of us, yeah.
Well, that's great. Well, Preston, this is awesome. Thank you so much for coming back and get working, because there's a lot for you to figure out, and it's very exciting.
Thank you, Richard. I enjoyed talking to you again. You always have good questions, make me think.
Excellent.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.